In this video, you're going to learn everything you need to know to be a productive developer when using Kubernetes. We already know what a container is, but it's time to decide how to deploy those containers to production. No ops person or no development team are going to spend their time SSHing into boxes and starting Docker containers. What we need instead is a container orchestrator. This part of the course is designed to teach you just enough Kubernetes architecture and how to interact with Kubernetes to make you productive and to be able to debug problems. Later videos will dive into how CPU and memory works inside Kubernetes and how it's different from using Docker directly or cgroups directly. Once we've decided to containerize our application using technologies such as Docker, the next question is this. Given a set of servers, our production servers, how do we decide which containers to run where? And how do we actually do it? How do we actually start the containers and manage their lifecycle? And that is what container orchestration is all about. The interface that you're going to have as a developer is just to say, I want 3 instances of this service or 4 instances of, say, my payment service. And it's the container orchestrator's job to use a set of servers and deploy those containers. The next thing that is solved by your container orchestrator is how to access those services. If you've deployed your application to some hosts that the container orchestrator manages, you also need to be able to access them. So we'll see how service discovery works both inside your environment and from the outside using ingress. And it doesn't stop there. Kubernetes and other container orchestrators also give us lots of other benefits, one of which is resiliency. So given that you're specifying a desired state, I want 3 instances of my service to be running, it's not just a deployment. What it is it's a statement that Kubernetes is going to keep true forever. So if a container crashes, it will be restarted. If a whole node goes in your cluster because someone turned it off or the node crashed, or perhaps you're in Amazon and they removed your instance, then it's the container orchestrator's job to restart your container and to potentially put it on a different node. And this has an important consequence for you as a developer. Your application must be able to handle your instance, the container, being restarted, being moved. It shouldn't be doing anything specific to that box that it's running on, and it should be able to shut down and restart gracefully. So what do we mean by this? Well, the fact that your application might get restarted and moved means that you need for your users not to notice. And the way of doing this is for all in-flight requests into your application need to be shut down gracefully. So you need to finish the current HTTP requests, or perhaps if you've got TCP keep alive connections on, then you need to stop requesting, you need to stop accepting requests and finish the existing ones. The other part to it is you need to be careful about what you keep in memory inside your container, because it might go away. And also typically requests, even from the same user, might end up going to a different instance of your container. So it's important to either make the container stateless. By that, I mean that the state is in databases or like a third-party external, say, in-memory cache, or you need to use technologies like Akka, which has features which mean that for all of the instances of your application, they can share the data and replicate the data, so it's not lost if one of your containers is turned off or crashes. And then next is elasticity. We might just declare that our current state is that we need 3 instances of this service and 3 instances of another service. But what happens if one of the services becomes overloaded? Then container orchestrators can be configured to look at the CPU or memory usage of your application and create more instances automatically. Or it could be a bit more manual, where they have the ability to scale your application. So you might start with 3 instances, but with a click of a button, we'd be able to scale to 6 or 9. Similar to this is we also need to handle rolling redeploys. So we've got version 1 of your application. It won't be long until you want to deploy new features or fix bugs. Inside container orchestrators, they typically support a way of rolling from one version to the next. So that means that it would stop one container of your application and then start another with the new version. And it would do this one at a time. Assuming that you handle graceful shutdown, this means that you can have no downtime for your users while doing deployments. Let's see how we specify what we want running to Kubernetes. In this case, we're going to be writing quite a bit of YAML. So the most basic thing we'll be doing is writing a deployment. A deployment has a few important fields. So the first is the number of replicas. So in this deployment for our server app, we're going to deploy 2 replicas. And then down at the bottom, we've got the image. So that's the Docker images that we've been building all along. There's some additional information, such as what ports are exposed. Another important concept in Kubernetes is labels. So when we say we want to describe a deployment with this many replicas, the containers are created with labels, in this case, server-app. And that is how the reconciliation works. The Kubernetes will then attempt to keep 2 containers with this label running indefinitely. That label will also be used when we define higher level services, which we'll get to in a moment. I've said containers up until this point, but Kubernetes actually adds an additional abstraction called a pod. And a pod is a group of containers that are always deployed together. So you could have your main container, which is your application, and you could always deploy something next to it, which might manage something like connections to a database. Or it could be a debugging pod, a debugging container, which means it has additional tools installed which allow you to inspect logs or inspect network traffic. Under the covers, containers inside the same pod can see each other, which actually means that they're using the same C groups and namespaces. So this is great because you're going to be able to interact with the processes from one container to another, but you also have to be careful. If you group a couple of containers together, one with your main application in, and then one with debug tools, they're in the same C group. So if you start using lots of memory inside that side container, the debug container, your main container might be killed because it might hit its memory limit. And let's just reiterate that pods and the containers inside those pods are ephemeral. They're going to come and go, both due to your rolling redeployments and internal things due to Kubernetes like nodes crashing and them being moved. And for most cases, you'll never address a pod individually. You can look it up. There are DNS requests that can look up individual pod IPs, and there's ways you can hit the Kubernetes API server to list all pods. But that's typically not how service discovery works inside Kubernetes. Instead, we use an abstraction called a service. And a service is a long-living, stable name for your group of pods. Or it could be pointing to something outside Kubernetes. It gets a virtual IP that won't change however many redeploys that you do. Once something is added as a service, it is added to DNS, so that other applications running inside Kubernetes can look it up. And in addition to that, you can also do service discovery via environment variables. So when I create a service which points to my application, my containers, other applications will have an environment variable with the virtual IP and the port to access it on. This is what a service looks like. It has kind service, some metadata with a name, and then the important part is the selector. That selector will match the labels on the pods. So if we create a deployment and we want the service on the left here to point to the pods of that deployment, the label needs to match up. So in our deployment, we've got labels, app is server app, and then the selector inside the service goes from app, server app. You could have multiple deployments with one service pointing to the pods of all of them. The other important part of a service are the ports it exposes. And in this example, we expose port 80 on the service. So that's how people will interact with us when the service is looked up via DNS. But the traffic is routed to port 8080 on the container. And this is nice because users expect to interact over port 80 for HTTP. But if your containers have decided to use some framework which by default uses port 8080, then this mapping can be done in the service. So let's have a look at how this would work in practice. So if we have a Kubernetes cluster here and we deploy one application, but we've got two instances, if a client application then wants to look it up, it would look it up via its service name. Then this is internal. Both the client and the server are running in the same Kubernetes cluster. The other type of access, the other way which we might want to expose our application, is outside of the Kubernetes cluster, perhaps to a different part of our organization or to the internet. And we do that via ingress. So if you want to just expose your application within your environment, within your Kubernetes cluster, then you can just use a deployment to create the pods and a service to expose it to other applications running inside that Kubernetes cluster. One thing in this diagram is I haven't depicted the service. There's no physical thing running which represents the service. It's just the routing of traffic. So this will depend on how your Kubernetes cluster is set up, but typically services are just implemented with virtual IPs and then routing via IP tables. If you want to expose it to the outside world, you create something called an ingress. Kubernetes ingress allows for access into your cluster. And you will not set up ingress for all of the applications you deploy inside your Kubernetes cluster. Many of the applications we build are just exposed within our own environment. So here's what ingress looks like. It's got a kind ingress, it has some metadata, and then it has rules. So the rules say that we expect traffic to be coming in on the host server app.info. And this is useful because one Kubernetes cluster can end up serving traffic for many, many different domains, and then we can match the paths. So we say anything that comes to /, so the root, is forwarded to this service, which is the service that we defined previously. One thing to note is that ingress is typically very proprietary to the type of cluster and infrastructure at your company. So the example we'll be using is using an Nginx ingress controller. Yours might look slightly different to this. The final thing to show you here is how you send and interact with a Kubernetes cluster. We'll be doing this in demos later, but the basic command is to use kubectl, which is the command for interacting with Kubernetes, and then apply -f and then the file of our YAML. We'll use the same command for services, deployments, ingress, everything, because they were completely self-describing. They had the kind inside the YAML file. We don't need to tell it at the command line which kind it is. A few common commands will be running as well. One to get pods, that will list the pods and all of the containers running inside them. If we want logs for a particular pod, then we use the kubectl logs command. If we want to get the information, the YAML back out of kubectl, out of Kubernetes, we can use kubectl get pod and then the pod name. And we can actually specify whether we want that output back as YAML or a text description or as JSON. And then finally, if we want to describe a pod state, then we use kubectl describe and then the name of the pod. So before we end the introduction to Kubernetes, I think it's important just to understand a little bit about the architecture, the internals of Kubernetes. So you know what happens when you send your YAML files into Kubernetes via kubectl. Everything about Kubernetes is about specifying the desired state, be it our ingress, our deployment, and our services. When we send that command, that information is stored in something called an API server, which is backed by etcd. Then the master component of Kubernetes has a set of controllers. And what these controllers do is they watch the data inside the API server, and then they act on that. So when we create a new deployment, it's not going away and creating all of the pods and containers directly. It's just storing the information in the API server. There's then a controller called a scheduler, which is reading that and then writing additional information back to the API server to say which containers should be running on which nodes. It's then up to the nodes themselves. There is a process called a kubelet running on every single node inside a Kubernetes cluster, which again watches the API server and waits to be told that it needs to run some containers. And once it sees that it needs to run some containers, then it starts them up. Kubernetes is very extensible, and it's extensible by these controllers. We've looked at a number of resources. We've looked at deployments, we've looked at ingress, we've looked at services. And there are controllers which read this information and then take action. And that is again how ingress works. One ingress controller might decide to set up Nginx every time you create an ingress, whereas another one might interact with your cloud provider. It could then set up Amazon load balancers or Google load balancers. It isn't imperative to know about this aspect of how Kubernetes works to be effective with it, but I do think it's very useful so that you understand that once your kube control command is finished, it doesn't mean that your containers are running. You can keep getting the status, and eventually those controllers and the kubelets running on the workers will have got your application to its desired state. That's it for the introduction to Kubernetes. Next, we'll demo everything that we've just described, and then we'll go into the details about how memory and CPU work for your containers running inside Kubernetes, and how it relates to everything that you've learned about Docker and control groups.